Hey guys, so the second half of this unit we're going to be revisiting systems of equations, and that's what this video is meant to get you reviewing, is how to solve a system of equations by both graphing and substitution. So as a review, a system of equations is simply two or more equations put together. And there are three types of solutions you can end up with when solving a system of equations. And we're going to look at this graphically so you can see visually how you get one of these three types of solutions. So most systems of equations only have one solution, and that solution is the ordered pair that is the intersection point of, in our case, two lines, because we're focused on linear equations. So if I had one line and then a second line, their intersection point, which would be an ordered pair xy, would be the solution of that system. There are, however, times when you could have two lines and you have no intersection point, and that's when you have parallel lines. So if you had lines that look like this system of equations would have no solution because there is no intersection point. And then there are also times when your two lines are actually the same line, one right on top of the other. And in this case, you have what is called infinitely many solutions because there are many intersection points when you have one line right on top of another one. So these are the three different types of cases that you could get with systems of equations. We're going to practice solving systems by graphing here on the front side, and then we'll get to the algebraic method of substitution on the back. So number one, I have the system y equals negative 5/3 x minus 6 and y equals 1/6 x plus 5. To solve these by graphing, it's pretty simple. You graph one equation and then you graph the other one. So our first equation, I'll do that one here in blue. We have a y-intercept at negative 6. Its slope is negative 5/3. So that equation will look like this. And when you are graphing these, it's really important that you use a ruler or some sort of straight edge, because when you're trying to find the intersection point, it's going to be very difficult if you did not use a straight edge for your lines. So there's the first equation. The second equation, which I'll do in red here, y equals 1/6 x plus 5, has a y-intercept at positive 5. Its slope is 1/6, so I can go up 1 and right 6, or I can also go down 1 and left 6. And we see that these lines cross at this point here. This is the ordered pair negative 6, 4, and so that is the solution of this system. Be sure you're writing down the ordered pair. Okay, and what that intersection point means again is if I plug negative 6 in for x and positive 4 in for y, that will give me a true statement for both of my equations. Okay, it works in both equations is what this ordered pair means. Okay, number two, y equals 5 and y equals 2x plus 7. Y equals 5 is a horizontal line through the y-axis at the point 0, 5. So this is what y equals 5 looks like. Y equals 2x plus 7. Well, that has a y-intercept at 7 and a slope of positive 2. So it looks like this. The intersection point of these two lines is this ordered pair that is negative 1, 5. Okay, number three, we have the equation 2y equals 8x plus 18 for our first equation. I need to get this in slope-intercept form before I can graph it. And so all I need to do is divide everything by 2 to get y by itself. So that's going to be y equals 4x plus 9. And then for the second equation, to put this in slope-intercept form, I need to subtract 24 from both sides. That gives me 4y equals x minus 24, and then I need to divide everything by 4. So I get y equals 1/4 x minus 6. And again, a straight edge is useful for these because obviously my lines here, since I did this downward part freehand, are intersecting perfectly. Let me put a few more points on here, and this blue line should be going through this same point here that the red line is going through. When you do this on paper, hopefully that looks a little bit nicer than what you see on the screen there. That ordered pair is -4, -7. So you should have the ordered pair -4 and -7 for this one. Okay, number 4, we have 3x plus 6y equals -12. I could graph this one by finding the x and y intercepts, or you can change it to slope-intercept form, either way. But if you find the x and y intercepts, we find that the x-intercept is -4, and the y-intercept is -2. So I could graph this line using those 2 points there, and I also see the slope is down to right 4 each time. So this is what my line looks like. And then y equals -1/2 x minus 5. We'll pass through a y-intercept here at -5. Down 1, right 2, and again, use a straight edge when you're graphing these, but hopefully you see that you get 2 parallel lines. These lines are never going to cross, and so this is actually a no solution. Okay, looking at the back side, we can also solve systems algebraically, meaning we can do it without graphing, and solving them without graphing is usually preferred over graphing simply because we don't always have graph paper or a ruler handy. So solving them algebraically, there's actually 2 methods for that. We'll look at the second method in the next video, but one method is by using substitution. And so substitution involves these 4 steps listed here. Your first step is to solve one equation for x or y. So we're going to look at number 5 and review how this works. In number 5, I have both equations solved for y. So this first step is already done for me. Y equals -7x minus 1 and y equals x minus 9. Step 2 is to substitute the resulting equation from step 1 into the other equation for that variable. So what that means is I need to take what y is equal to, and I can choose either equation for this. I'll choose my second one here. So since y is equal to x minus 9, I substitute this quantity, x minus 9, in for y into my other equation. So that gives me x minus 9 equals -7x minus 1. Step 3 is to just solve for the remaining variable. So I have x in this equation that I'm going to solve for now. So if I add 7x over the equal sign, I get 8x minus 9 equals -1. And then I can add 9 to both sides to get 8x equals 8 and divide to get x equals 1. Once I have solved for this remaining variable, then my last step is to substitute this answer, x equals 1, back into either original equation to find the other variable, in this case y. So I'm going to take one of these original equations, I'll just take the second one, y equals x minus 9, and now that I know that x is equal to 1, I can substitute that in for x and solve for y. So I get y equals 1 minus 9, and therefore y is equal to -8. So the ordered pair for this system would be 1, -8. Number 6, y equals -5x plus 30 and 7x plus 3y equals 42. The top equation is solved for y already, so I'm going to take what y is equal to, -5x plus 30, and I will substitute this expression in for y into my second equation. So when I rewrite my second equation, it will look like this. 7x plus 3 times the quantity, negative 5x plus 30, equals 42. So solving this equation for x, we get x equals positive 6. Now to find y, I need to take one of my original equations and substitute positive 6 in for y. So I can choose, again, my first equation, y equals negative 5x plus 30. I know that x is 6. So this becomes y equals negative 30 plus 30, and y comes out to be 0. So this ordered pair that's the solution of this system would be 6, 0. Okay, 2 more to try. In number 7, I have 2 equations, and none of them have a variable solved or isolated. And so when this is the case, we want to pick the easiest variable it is to solve for. And that's going to be the variable that has a coefficient of 1 or negative 1. In this case, the only variable that has a coefficient of 1 is the x in the top equation. And so I'm going to solve for x in this top equation, and all that's going to involve is adding 7y over the equal sign. So this gives me x equals 7y plus 53. So just remember, you don't always have to solve for y. Okay, when we're doing substitution, we're not necessarily putting our equations in slope-intercept form. We're just solving for one of the variables, and in this case, x is easier to solve for than y. So since I know x is equal to 7y plus 53, I'm going to substitute 7y plus 53 in for x into my bottom equation. Make sure you plug in for the right variable. So this will be negative 4 times the quantity, 7y plus 53, minus 5y equals 19. I distribute on both sides, I get negative 28y minus 212 minus 5y equals 19. And then I solve this equation for y. And so when I divide both sides by negative 33, I get y equals negative 7. So now I pick one of my original equations, either one. I'll take the first one again and substitute negative 7 in for y. So this becomes x plus 49 equals 53. And so that means x is equal to positive 4. So the ordered pair for this system is 4, negative 7. Again, we always start with x, then y, so 4, negative 7. Okay, last one. 2y equals 6x plus 10. 3x minus y equals negative 5. If you look at the second equation, y has a coefficient of negative 1. So to solve for y in this equation, I can subtract 3x from both sides to get negative y equals negative 3x minus 5. And then if I divide everything by negative 1, I get y equals 3x plus 5. You could have also divided everything by 2 in the original equation. That would have also isolated y in that equation. That's perfectly fine to do. Just keep in mind sometimes your numbers won't be as nice and you might get fractions involved. So you want to solve for the variable that's going to allow you to avoid fractions essentially. Okay, so just keep that in mind when you're doing the substitution method. So we use the second equation to get y by itself. So I need to plug this expression into my first equation for y. So it's going to go right here. So this is going to be 2 times the quantity, 3x plus 5 equals 6x plus 10. And now I solve this equation for x. So I get 6x plus 10 equals 6x plus 10. If I attempt to solve this for x and subtract 6x from both sides, I notice I get the statement 10 equals 10, which typically isn't all reals when we're solving equations. We don't write all reals for this. We actually write infinitely many solutions. So what this means is you can't just pick any ordered pair and have that be a solution for the system, but there are an infinite number of ordered pairs that would work as solutions. Okay, so that means if we were to graph both of these lines in the same coordinate plane, we would get basically the same line, one on top of the other one. So any ordered pair on that line could be a solution of this system, and so that's why we use the phrase infinitely many solutions. Okay, so it's this case whenever you solve the equation, the variable goes away and you get a true statement, is when you get infinitely many solutions. Okay, as always folks, if you had any questions over this video, even though it was review, make sure you're ready to ask those the next time you're in class. Until then, have a nice day. You are all wonderful people.